All right, let's continue talking about geometrical optics. So, uh, in the last lecture, we talked about the reflection of light, and we talked about how we can form an image with a plane mirror and the characteristics of the image inside the plane mirror. Okay, so this time we're going to continue talking about the reflection of light on spherical mirrors, either a convex mirror or concave mirror. Um, and those spherical mirrors can also be used to form an image. So we're going to use ray tracing to figure out the size and direction and the position of those images. And then we're going to derive this mirror equation to quantitatively describe the size, orientation, and position of the image. And then at the end of the lecture, we're going to cover the refraction of light. And then in the next and last lecture, we're going to do ray tracing for lenses to figure out how we can use lenses to form images. And then we're going to derive the thin lens equation to quantitatively describe the imaging with lenses. Okay, so let's first review what we learned last time. So we're talking about geometrical optics. So light is a wave. Um, but we're going to talk about the simplest aspects of light, where we can treat light as rays. Okay, so the relationship between the wave nature and the rays of light is displayed in here. Basically, the relationship between wavefronts and rays. If you have a point source of light, you can emit light towards all directions. If you plot out the peaks of a light wave at a certain time, you will see all those concentric circles. Okay, those are called wavefronts. And then if you want to display the propagation of light, you're going to have all those rays. Those rays are radial and straight lines from the source of light. Okay, and one thing to notice is that those wavefronts and those light rays are perpendicular to each other. Okay, so when we're talking about geometrical optics like reflection or refraction, we can forget about all those wavefront and we can talk about light going in those straight rays. Okay, but we should always keep in mind that light is actually a wave and you can always recover the wavefronts from the light rays. Okay, so you should always keep in mind that there are oscillating electric field and magnetic field in space, and light is propagating towards a direction, and then the electric field and magnetic field are perpendicular to the propagation direction. All right. And one important case of the light rays is when you are very far away from the light source. Okay, in this case, we can treat the wavefronts as planes. So we have plane waves, and then all the light rays are parallel to each other. Okay, but we still have those light rays perpendicular to the wavefronts. Okay. Okay, so in the geometrical optics, we treat light as rays and they go through straight lines. Okay, but there are a few cases where light is having doing something at the interface. And the first important case is reflection. Okay, so reflection happens when you have a surface like this, and then you have incident wave. We learned that law of reflection tells us how we can determine the reflected wave. So we find out where the incident wave is incident on this surface. We draw a perpendicular line, which is called surface normal. And then the incident wave and surface normal defines the plane of reflection, which is the green plane. We know that the reflected wave should be within this plane defined by incident wave and surface normal. Okay, and furthermore, the law of reflection tells us that the angle of incidence and angle of reflection, defined as the angle between the incident wave and surface normal and reflected wave and surface normal, they should be equal to each other. Okay? So one thing to notice is that the angles are defined with respect to the surface normal, not with respect to the surface itself. So if you uh, uh, make a mistake and talk about the angles with respect to the surface itself, then you're going to be 90 degrees minus the angle you're talking about. Um, so if we have a smooth surface, we can have a specular reflection, and all the parallel light will be parallel light. Parallel incident light will be parallel reflected light. Okay, and we described how we can quantitatively describe this imaging process. Okay, so we can consider an object in front of a mirror, a plane mirror, uh, a certain point on the object can emit light along different directions. And we see that after reflection by this mirror, these light are not converging. Okay, instead they're going towards a larger range of angles. Okay, but then if you put an imaging system in here, for example, your eye or a camera, you can actually extend all those light rays. Okay, when you extend all those light rays, they actually converge on a point that's behind the mirror. Okay, and so if you look at the object through the mirror, it looks like the all the light is coming from a image inside or behind the mirror. Okay, so the light ray doesn't actually go behind the mirror, but it looks like there's an image behind the mirror and is emitting all those light rays. Okay, so we learn from here that the plane mirror can form an image. The image is virtual because no light rays actually goes into the image. And then the object distance and image distance are equal, and then the size of the object and the size of the image are equal. Okay. Okay. And we learned that all those properties can be derived from geometry and law of reflection. So that is why it's called geometrical optics, right? So we can consider two rays, one ray going from the object and going through a arbitrary angle theta hits the mirror and get reflected into the imaging system. A second ray will go perpendicular to the mirror, and when it goes perpendicular to the mirror, it will be exactly reflected back. Okay, and then if we extend the line, those two lines of the extended lines of two reflected light, okay, will converge at one point behind the mirror, which is P prime. Okay, and then we consider those two triangles PAQ and P prime AQ. We find out that they share this same angle, same right angle, and then share this side. So from angle, side angle, we find out that the triangle PAQ is exactly the same as triangle P prime AQ. So from there, we derive that the PQ should be the same as P prime Q. Okay, and also we derive that the height of the object should be the same as the height of the image. So those are the characteristics of image forming with a plane mirror. So we summarize all those things in here. The mirror image appears to be the same distance and is the same size. Okay. One tricky thing is that if you consider an error in front of a mirror, okay, if the error is pointing parallel to the mirror, then it will form an image that is basically the same. Okay. But then if you have an error that is perpendicular to the mirror, then the image basically flips from the object, right? So, and a mirror actually keeps the upright position, but flips what? It flips from this situation, we find out that the mirror actually flips uh, the front and back, right? Flips front and back. And now if we're talking about the person, and we always define the left and right with respect to the front or face of a person. We find out that the image actually reversed right and left. Okay, but the mirror actually doesn't know which direction is upright or left and right. It only knows two directions. Right, the first direction is parallel to the mirror, then the object's not going to be changed. Second direction is that perpendicular to the mirror, then the object is going to be flipped. Right. So the mirror keeps this planar direction, but then flips the perpendicular direction errors. Okay, and those two properties are also derived from the fact that the mirror forms an image at the same distance and same size, right? Okay. Okay, so a special case of a plane mirror is that you can have a corner reflector, and a corner reflector will reflect, will send the ray back to the exactly the same direction. Okay, you can have a three-dimensional corner reflector. You can have a two-dimensional corner reflector. For the two-dimensional case, you should be able to prove that the incoming ray and the reflected ray are parallel to each other by simple geometry. Okay. And then we talk about those spherical mirrors. Okay, so plane mirror is a plane, but we can also cut a mirror from a sphere. Okay, in this case, we'll have a spherical mirror, and then immediately we will see the inner surface and outer surface are different. Okay, and depending on which surface we coat a highly reflective material like silver, we can either have a concave mirror, while the reflecting surface is concave and its inside surface, or we can have a convex mirror where the reflecting surface is outside surface and is convex. Okay, and they have similar but different properties. Okay, and further we define the center of curvature. Center of curvature is basically the center of this sphere where they cut the mirror from. And then the distance between the center of curvature and the mirror is basically the radius of this sphere. We further define this principal axis. Principal axis connects the center of curvature and the center of this spherical mirror. Okay. So we sending a plane wave or parallel rays, and we see how it get reflected from a convex mirror. Convex mirror is a spherical mirror where the outer surface or the convex surface is coated. And so we see that the light rays actually diverge. Okay? It goes into the mirror as parallel light rays, but when they get reflected, they reflect towards a larger range of angles. So it get diverged. But then if we extend all those reflected lights, we can see that they will mostly converge on the same point behind the mirror. Okay, and this point is called focal point. And we derived the expression for the focal length, right? So we can have this kind of light ray parallel to the principal axis. This is principal axis. This is the light ray we're talking about. It makes an angle theta with the mirror surface. Okay, and then the law of reflection tells us the angle of reflection is the same as angle of incidence. Okay, so now we extend this reflected light rays, okay, and cross the principal axis at point F. Okay? And if we connect this point A and the center of curvature, we know the distance is exactly the radius. Okay, and we know that this angle is theta, and also this angle is theta because we have a light ray. This light ray is parallel to the principal axis. Okay, so this angle equals this angle. Okay, now we have a triangle with two angles. Okay, the same. So we have two legs the same. Okay, so AF equals FC. Okay? And the size of it, we can draw a perpendicular line from F to AC. Okay? And we find out that AF is basically R divided by 2, and then further divided by cosine theta. Okay? And this is the same as FC, okay, because the two legs are the same. So at the end of the day, we'll find out that length of BF is basically BC, which is R, minus FC, which is R divided by 2 cosine theta. And we find out that if theta is small, this will go to R minus R divided by 2. So it's R divided by 2. And that is a small and that is a fixed value, small theta. So if we have parallel rays going towards this spherical mirror, it will be reflected. The reflected light will diverge. But then if we extend the lines, and if the angle theta is small, the lines will cross the principal axis at the same point F, and the distance between this point F and the mirror is called the focal length, and it's a fixed value of half r, okay, where r is the radius of this spherical mirror. We further have a minus sign in front of this focal length, and we can see a sign convention in here. Okay, so if there is a minus sign, that indicates that the focal point is behind the mirror. Okay, so we do not actually focus the light onto the point F. Instead, we have a diverging ray going. Reflected rays are actually diverging, but then if we extend the reflected rays, they will converge at point F. Okay, so this F is a virtual focus, and then this this focal length has a minus sign in front of it. And the same thing happens for the concave mirror, okay? But it is a little bit different, okay? So we have a concave mirror, the inner surface is coated, and so we can shine light towards, we can shine parallel light rays towards the concave mirror. We see that they will be reflected, okay? They will be reflected. And then if we connect the point where the light ray hits the mirror and the center of curvature, we see that this distance is basically radius r, right? And if we look at this angle is theta, because principal axis is parallel to those light rays. So this angle is equal to this angle. And then if you draw a line, perpendicular line from F to this radius, you can derive that this side is same as this side, and they are r, again, r divided by 2 cosine theta, right? So the length, the distance between the focus point F and the mirror is r minus r divided by 2 cosine theta. Okay, and again, if theta is small, this will go to r divided by 2. Okay, and it's a fixed value. So if we talk about all those light rays that makes a small angle with respect to the mirror, then the light rays will get reflected, actually converge onto the point F. Okay, and the point F is the distance half r away from the mirror. Okay, so in terms of a concave mirror, we actually have light rays converge into the point F, and so the distance is still half r, but there is a plus sign in front of this focal length because we actually have light rays focused onto this point F. Okay? So plus sign indicates that the focal point is in front of the mirror. Okay? Okay, so if you have a mirror like this, you know this side is in front, and this side is behind. If you stand in front of a mirror, this uh, the other side of the mirror is behind the mirror, right? This is easy to understand. Okay. So we have a problem here. Suppose you would like to use the sun to start a fire in the whiteness. Which type of the mirror, concave or convex, should work best? Okay. So we have those two drawings. One is this concave mirror on the left, and then this convex mirror on the right. Okay. So they both have a focal point, okay? And the focal length are both half r, okay? but there's important distinction between those two cases. In the case of concave mirror, okay, concave mirror, the light rays, the reflected light rays will actually converge, right? Converge. Converge means that they will actually go to the same point, F. Okay? But if you use this convex mirror on the right, the light rays actually diverge. Okay? Diverge. Diverge means that the light rays will span a larger angle than the incident light rays. So you can see that it points towards up, it reflects back, and then there are also light rays pointing downwards. Okay? So the light rays are diverging. And if you want to focus the sunlight onto a single point so that you can light up a paper, you should probably use this concave mirror. Okay, concave mirror. They will bring all the light rays together at the point, and then this point has a high energy. You can start a fire in here. Okay, so a concave mirror is the one to use. Okay. And as what we derived this point where the reflected light rays crosses the principal axis, the distance between this point and the mirror is actually r minus r divided by 2 cosine theta. And only when the theta is small, okay, and theta is the angle of incidence or angle of reflection in here, doesn't matter, or it's the angle between the light ray and the principal axis. And only when theta is small, this is a fixed value of half r. Okay, when theta is large, we can actually see that theta is large, cosine theta is small, and this r divided by 2 cosine theta is large, and then this distance r minus this thing is getting smaller. Okay, so for large theta, the light rays is going to cross the principal axis at a shorter and shorter distance from the mirror. Okay, goes towards this way when we increase the angle of incidence. Okay, in other words, if the ray is further away from the axis, it will make a larger angle with the mirror, and then it will miss the focal point more. Okay, the point that it crosses, the point that the reflected light crosses the principal axis gets closer and closer to the mirror. So this tells us it will give us a blurred focus. So if you want a sharp focus, you can reduce all those light rays of large angles and only keep the light rays of small angles. And then those small angles will follow this formula, and the focal length is about half r. And those rays are called paraxial rays. Paraxial rays will help you make a sharp focus. Okay? And you can also see this phenomena in this cup, and you shine sunlight from above. Okay, sunlight is basically reflected by the wall, and the wall of this cup is basically a concave spherical mirror. Okay, it will be reflected towards the bottom of this cup. Okay, and we see that this wall of cup has all those angles of incidence or angles of reflection. Okay, so those paraxial rays will converge on this point. This is a bright point in here, but then those those rays that are farther away from the axis, like this ray, will actually cross somewhere further away, okay, from the focus and closer to the wall of this cup. Okay, so at the end of the day, you see this this kind of pattern when you put the cup on the sunlight, and tells us about this spherical aberration. Okay. So as we know, if we use a spherical surface, okay, there is a spherical aberration, and the further away rays will not reflect towards the focal point. Okay, it will cross the principal axis in here. So you need to adjust this surface curvature when it's further away from the principal axis. Okay, so it cannot be a uh, spherical surface, but you need to adjust it depending on how far away you're from the principal axis, so that the reflected light ray can actually go to the focus F. And mathematically, we can actually prove that this shape that has a perfect focus is parabolic. So the actual proof involves derivation of the tangent direction of the surface. So it relates to the calculus, and it's not required in this course, but you need to know that if you have a parabolic mirror, then the parallel rays will actually converge towards the same focal point. And this is strict. It doesn't matter how far away this ray is from the principal axis, the reflected ray will always go through this focal point. Okay, so the parabolic mirror has a single focal point and it doesn't have spherical aberration. Okay, and this so if we want to form a perfect image with a concave mirror, we need to make a large parabolic mirror. Okay, and this is what we use actually in the Hubble Space Telescope, HST. Okay, so we need to have a perfectly parabolic mirror in here, and it forms a perfect image in here. Okay, so similar to the planar mirrors, those spherical mirrors can also make an image. Okay, and we're going to learn how we can derive the this image from this technique called ray tracing. Okay, so we can talk about a few special rays in here. Okay, so there is this parallel ray called P ray. It's going parallel, and we know that parallel rays reflected by a spherical mirror will go through the focal point. Okay, so this ray we have very good knowledge of it. This is a blue ray, P ray. Okay, parallel ray. And then we have those F ray. F ray means focal ray, and this ray goes through the focal point. And we know that if a ray goes through the focal point and it hits the spherical mirror, it will be reflected as parallel rays. Okay, so if we know a ray, we have a F ray, we know how it's reflected by the spherical mirror. And the third ray that we know the trajectory is the C ray. C ray means the center of curvature ray. This ray goes through the center of curvature, so when it hits the spherical mirror, it actually makes a right angle with the surface. Okay, so angle of incidence and angle of reflection are both 0 degrees. Okay, or in other words, the light ray is perfectly reflected towards the original direction. Okay, so if we have an object, we can always draw its P ray, F ray, and C ray. And for those three rays, we know how it will be reflected by this spherical mirror. And if we want to know the image formed by a system, okay, so as what we did in the planar mirror, we find a point in the object, okay, we find out different light rays going from the object, and then it somehow goes through a imaging system. Okay, this imaging system could be a mirror, could be a spherical mirror, could be a lens. We're going to talk about that in next lecture. And then all those light rays should converge into a single point of P prime. Okay, in this case, we say that P is forming an image at P prime. Okay? And if we have an object, we can do this for every point in the object. We can call it P, and it will form a image in the position of P prime, and then we know this whole object is forming an image here. Okay. So how do we do this for a concave spherical mirror? Okay. We're going to talk about that very soon. And this is the case for the convex mirror. Convex mirror, we can also talk about those three rays, P ray, F ray, and C ray. Again, P ray is parallel. It gets reflected by the surface of the convex mirror. But then if we extend the reflected ray, it will actually converge into this focal point, right? And we learned that the distance, the focal length is about half r. Okay? Now, if we have a ray that actually goes towards the focal point, it actually will get reflected and go back towards parallel direction. And this ray is called F ray. This is a focal ray. And the third ray that we know the direction is the C ray. It actually goes towards the center of curvature. And in this case, it will make a right angle with the surface, the angle of incidence, angle of reflection, both 0 degrees, and the ray will be perfectly reflecting back towards the original direction. Okay. And ray tracing just means that you can pick a point from the object. You can draw the P ray, the F ray, the C ray, and we know how they will get reflected by a mirror. And then we can trace whether they, where they form an image. Okay, for example, for this convex mirror, okay, we care about this point P, or maybe I should call it A in the object. Okay, and does it form a image A prime behind this convex mirror? So we draw a P ray that is parallel to this principal axis, and we know that the reflected ray should go through this direction. Okay, so P ray hits the mirror at this point. We connect this point and the focal point. We extend it. We know that this is the direction of the reflected P ray. Okay? Similarly, if you have an F ray, okay, so you connect this point A and the focal point F, you draw this F ray. The F ray is gonna hit. F ray is gonna hit. Sorry. F ray is gonna hit the mirror in here, and after it gets reflected from the mirror, we know it should be a parallel light. Okay? So if we extend this parallel light, we have this green dash line in here. Okay? And we say that the green dash line and the blue dash line actually cross at the point A prime. Now if we draw a third ray of C ray connecting the point A and center of curvature C, we have this C ray. The C ray will be perpendicular to the surface of the mirror and it will reflect back. And if we extend the C ray, we have this dash red line behind the mirror. And we see that the dash red line, the dash green line, the dash blue line actually converge onto the same point A prime. Okay? So if we have an imaging system like an eye in here in front of the mirror, we are gonna collect the reflected P ray, the reflected F ray, and the reflected A ray, the reflected C ray. And although those rays are diverging, it looks like they're coming from the same point A prime. Okay, so in this case, the object is forming an image behind the mirror. The image is virtual because no light ray actually goes behind the mirror. Those are all dashed lines. And the image is actually upright. Okay, and we can also see that the image is actually smaller than the object. Okay, so this is telling us if we use this ray tracing technique, we draw the parallel lines, we draw the focal lines, we draw the center of curvature rays, we can figure out how they get reflected by a mirror. We can figure out the size of the image, the position of the image, and the orientation of the image. Okay, So in case of the convex mirror, it actually forms a virtual image. The image is upright, and the image is smaller than the object. Okay, so how does it work for a concave mirror? Okay, so before we talk about concave mirror, we have one more thing. So if you form an image with a convex mirror, okay, so we actually two lines tells us a single point, right? A prime. So we don't need to draw the C ray. We can just draw this P ray. Okay, this is the blue ray is the P ray. It gets reflected by the mirror. The reflected line should follow this direction connecting the point of incidence and the focal point. And then we draw this F ray. F ray goes along the line AF, and it gets reflected and be parallel. Okay, so we extend this parallel line from the angle of instance on this mirror, and then this dash green line and the dash blue line converge at the same point A prime. Okay, now the one thing we can do is that we can move the object back and forth. Okay, if we move the object back and forth, what we will see is that the object will always be at the same height. Okay, the A point will always be at the same height. So if we draw a P ray, which is parallel to this principal axis, it will always hit the mirror at the same point. Okay, so the result is that this blue dash line, the extended reflected P ray, will always be the same line, okay? Regardless where you put your object. But the other F ray will actually move, right? So F ray connects the A point and the F point, and if you move A point further away, this F ray is gonna cross the mirror at a lower point. Okay, if you move this object A further away, this crossing point will move downwards. Okay, crossing point will move downwards. So the crossing point moves downwards and it gets reflected and be parallel, and you extend this parallel line to be this green dash line. The green dash line is actually going to make a cross section with this blue dash line at a lower and lower position. So this is telling us that if you move the object further away from this spherical convex mirror, the image you're going to form is going to be smaller and smaller. Okay, and the other thing is that the image is always upright and it gets closer and closer to the focal point. Okay, we can draw a even further away object. For example, we talk about this mirror and we draw the object in here, right? So again, the P ray will always be hitting the mirror at the same point, and this blue line is always going to be the same. But then the F ray will be different. Okay, to find the F ray, we connect the point A and the focal point, and it crosses the mirror at the lower point, and then at this lower point, the F ray gets reflected to be a parallel light. We extend the parallel light, find out the cross section with this blue dash line. We see that the cross section point moves to lower position. Okay, so this tells us the image that is formed is getting smaller and closer to the focal point. Okay, so this is about the image formation with a convex mirror. We see that if we draw the P ray, F ray, and C ray, we can figure out where the image is. Okay. Now, we talk about image formation with a concave mirror. Again, we can just draw, we have object in here, we have a point A in the object. We can just draw a P ray. The P ray is blue ray and it's parallel to the principal axis. It hits the mirror and then it gets reflected. The reflected light should go through the focal point. Okay, so we know where the reflected light is. This is a blue line. And then we draw a F ray from the point A. We connect point A and the point F. That is the F ray. F ray will hit the mirror, and then because it goes through the focus, it should hit the mirror and get reflected as a parallel light. Okay. Now, if we look at the green line and the blue reflected ray, they will cross at one point, and this point tells us where the image is. We can see that this image point is actually below the principal axis. And if we do this for different points on the object, we can see that all those points will be imaged to a point that's below the principal axis. In other words, the image is going to be flipped. It's going to be the opposite direction of the original object. Okay. The second thing is that we see that the light rays actually converge on this image, which tells us that the image is actually a real image. Okay? If you actually put a cardboard in here, you can actually see an image on this cardboard, right? So this is a real image where the light rays actually converge. Third thing is that if you put the object further away from the center of curvature, you will see that the image is actually smaller than the object. Okay. Now, if you move the object closer to the mirror, again, the P ray is still the same because the object is the same height. The P ray will still hit the mirror at the same height, and then it will go through the focal point. Okay, so the blue line is the same. But when you move the object closer to the mirror, what happens is that the F ray will actually make a larger angle with respect to the principal axis. And it will hit mirror at a point that is much lower. Okay? Hit the mirror at a point that's much lower. And then it will be reflected from the mirror at a point that's much lower. Okay, so if we consider this reflected green light, it will cross the fixed blue light at a position that's even lower. So which means that the image will get larger. Okay? If we move the object closer to the mirror, the image will get larger. Image get larger, and also the image gets further away from the mirror, right? Because the crossing point is sliding on this blue line. Right? The crossing point slides to this point. Okay? And on the left, the crossing point is on this point. And in either case, we are always forming a real image where the light rays are actually converging onto this image point. Okay. So if you put the object beyond the center of curvature, as in case A, you will form an image that's smaller than the object and is between the point C and point F. Now, if you put the object between point C and point F, then you're going to form an image that is beyond point C, and the image is going to be larger than the object. Okay. And what happens if you put the object just on point C? You can probably guess, right? It's just between this case A and case B. And in this case, you will connect this point and the focal point. You will hit the mirror and become parallel rays. Okay, you will cross this blue point exactly at the position of original object. Okay, and the image and object will be exactly at the same point C. Image is inverted, but is of exactly the same size of the object. Okay. Here. Okay, so here we have a problem. So passenger side rear view mirrors in new cars often have the warning label that read object in mirror are closer than they appear. Are those rear view mirrors concave or convex? Okay. The first thing we notice that is that if we're on a car and we look at the rear view mirrors, all the image inside this rear view mirrors are upright image, right? So if you sit on the car, you look at the side image, you can see some cars in there. Maybe I should go online to show you this. Okay, rare mirrors. Let's see, you can see some image. Those rare mirrors are what? They're forming an upright image. Okay, the world is not upside down inside this rare mirror. So what tells it? This tells us that it cannot be convex mirrors, right? Because we can go back to our slide. We see that the convex mirrors always form. Sorry, cannot be concave mirror, right? Because we just talked about the concave mirrors. Concave mirror always form an image that is upside down. Okay, but in the rare mirrors, it is an upright image, so it cannot be the concave mirrors. Can it be a convex mirror? So if we have a convex mirror, okay, there's object, in this case is a car behind us. Car is forming an image inside this convex mirror. It is an upright image that checks, and the image is smaller than the object. Okay, so if the image is smaller than the object, then we perceive it as if the image is further away from us. Okay, so this is consistent as this saying that the object in the mirror are closer than they appear. In other words, the image looks small, so the object appear as if they are far away from us. Okay, so those mirrors are actually convex mirrors. So in the convex mirrors, we form a upright image, and the image is smaller than the object. So, so it appears, the image appears further away from the mirror. Okay. And one thing I want to note, uh, clarify or remind you is that we just talk about the ray tracing for concave mirror and also for convex mirror. And I want to tell you that it also works, of course, for a plane mirror, right? So how do you do ray tracing for a plane mirror? For plane mirror, you can do a P-ray, okay? So let's say this is point A. You do a P-ray like this. What happens? For a plane mirror, a P-ray will make a right angle with the plane mirror, so it will be reflected back, okay? So if you extend this line, you will have this kind of line behind the mirror, okay? And then you draw an arbitrary ray, okay? You draw an arbitrary ray, it will make an angle theta with respect to the surface normal, and then it will be reflected also at an angle theta, okay? So this is telling us that a normal plane mirror will also reflect the rays, so they are diverging. But we can always trace those rays back, right? So we extend this ray back, and we see that those two lines will cross at the point A prime. Okay. Now just like as what we talked about last time, this angle is you can find out that this angle is the same as this angle. Okay, and we also have two right angles and a shared side. So by the A angle side angle, we know that the triangle ABC is the same as triangle A prime BC. And from there, we derive that AC is equal to A prime C. Okay? And we can also derive that the image size is the same as the object size for a plane mirror. Okay, so the ray tracing also works for a plane mirror. Okay, okay. Now there are so many cases in the ray tracing, right? So there is plane mirror, there is convex mirror, there is concave mirror. Concave mirror, you can put object beyond C, you can put object between C and F, you can put object within F, okay, something like that. And it is important to make some general statement. Okay? So if we have a point, okay, this is a point from our object, and the light from the point is diverging, then we have a real object. We call it a real object. Okay. If on the other hand we have light rays reflected and they converge onto the same point, then we have a real image. Okay? This is a case for the concave mirror, right? But then if we have all the light rays diverging, okay, they're going through a large span of angle, but we extend those light rays and they converge at the same point, okay, behind the mirror. Then we say we have a virtual image. Virtual means that the light ray actually does not converge onto the same point, but the light rays are actually diverging. But if we put the imaging system in here, it looks like the light rays are actually from a single point, and this point is called the virtual image, right? And similar to virtual image, we can also have a virtual object. For example, if you have the converging light rays, so they cannot be from a single object on the left, right? So they cannot be from a single point from the left, because the single point will always emit this diverging patterns. So if we have converging light rays and they're converging onto the same point on the other side of the mirror, we say that we have a virtual object. Okay. So either it's real or virtual, depends on whether you actually have light going through this point, right? We actually have light going from the object or converging at the image, then you have a real object or real image. If you don't actually have a light ray from this point, then you have a virtual object. If you don't have light rays going from this point, then you have a virtual image. Okay. And we can also summarize the imaging characteristics of convex and concave spherical mirrors. Okay. So we can put our object at different locations, and we talk about the image orientation, image size, and image type, right? So for convex mirror, okay, what is a convex mirror? Remember, convex mirror is like this, and the parallel light rays will get diverged, but then we can extend onto the other side of the mirror, okay? So for convex mirror, the image is actually upright and the side is reduced. It's a virtual image because no light ray will actually go to the other side of the mirror. Okay? And for concave mirror, the situation is more complicated. For concave mirror, if you put the object beyond C, you will have an inverted image. Okay, you have an object in here, you have an image in here. The size is reduced by this, but it is a real image because the light ray actually goes through the image. If you put the object on C, you have still an inverted image, but the size is exactly the same as the object. Okay. If you put the object between F and C, you still have an inverted image, but then your object is further away from C and is enlarged. Okay, the enlarged image. And we will talk about putting the object inside F. Then in that case, you will have a virtual image, which means the image is on the other side of the mirror and no light is actually going through there. Okay, but this image is upright and virtual. So a convex mirror always makes a virtual image and is always reduced in size, always upright. But the concave mirror can make either real image or virtual image, depending on where you put your object. Okay, so this is the convex mirror, and the convex mirror makes a upright image. The image is on the other side of the mirror. The light rays are actually diverging, but if we extend the light rays, they will cross at the same point. Or in other words, the light rays looks like they're from this image. Okay, so the image is a virtual image, is upright and is reduced in size. Okay, and then if we look at the concave mirrors, it depends on where you put your object. If you put your object outside C, put object in here. Again, you can draw all those rays and do ray tracing, but the two most important rays are this P ray number 1 and the F ray number 2, right? F ray number 2. And the P ray will go through F after reflected. The F ray will be parallel after reflected, and we can find out where they cross, and that tells us where the image is. Okay? So if you put your object outside C, your image is going to be between C and F. The image is inverted. It's a real image, but it's reduced in size. Okay. Now, if you put your object exactly at point C, again, you can do ray tracing with the P ray and the F ray, and you see that your image is exactly at the point C, and it's exactly the same size. It's a real image, but it's upside down. Okay. And we can prove it easily if you just do ray tracing, okay, for this number 4, right? So number 4 is where you connect the point Q and the point V, where the principal axis makes a cross section with the mirror. And this light will, of course, be reflected by the mirror and go through the same point Q prime. And if you look at this whole situation, you can see that this situation is perfectly symmetric along with respect to the principal axis. Okay, just label it as axis. Okay. So in this case, we have those two sides the same, those two angles the same. Everything is the same, right? This angle of incidence, this is angle of reflection, this edge is the same, this edge is the same, and so on and so forth. So everything is symmetric with respect to this principal axis in this case. And so you have a exactly same size image as your object. And now if you put your object exactly at the focus, F, okay, what happens is that you can do this ray tracing for P ray. P ray will be going through F after reflection. You do this ray tracing for this number 4 ray. It goes through the point V, and it reflects at the same angle towards number 4. You can also do this ray tracing for a C ray. C ray is going through the center of curvature C. It will hit the mirror at the right angle and reflect back. And what you will see is that all those rays, all those reflected rays, are parallel to each other. Okay, so this tells us that you cannot form an image anymore if you put an object at the focal point. Okay. A more fancy way to say this is that your object is forming at infinitely long distance, okay? Or your object distance is infinite, or your image distance is infinite, sorry. Okay, now if you put the object inside focal point, okay, inside focal point, okay, just inside focal point. And if you put object inside focal point, you can do this ray tracing again with the P wave. This is the number 1 wave. P wave is parallel to the principal axis. It gets reflected. Reflected light goes through the focal point, right? Goes through the this is a purple line here. We can extend the reflected light, and it will go through the point Q prime. Okay. And the second ray that you care is F ray. F ray is number 2. Number 2 is F ray. This is green here. So F ray is connecting point Q and point F, and F ray is going to hit the mirror and then be a parallel reflected light. Okay, you can again extend this parallel light, and we see that the dashed green line and the dashed purple line will converge at point Q prime. And this point Q prime is on the other side of the mirror. No light actually converge on Q prime, but it looks like that reflected light 1, 2, 3, 4 are from the same point Q prime. Okay, so Q prime is a virtual image. Okay. And we can see that this virtual image is actually larger than the object. Why is that? Uh, because you can determine the position of Q prime from the P ray and the F ray, right? And in this case, if you put the object inside focal point, you can see that if we connect the focal point and the object, this light ray is always going upward. Okay? The light ray going upward, it will cross the mirror. It will hit the mirror at the point that is higher than point Q. Okay, and then it becomes a parallel light. Okay, and the image is just on the extended line in here. So we know that the Q prime must have a higher position than Q. So this tells us that this virtual image is actually larger than the object. Okay. And the other thing you can observe is that if you move this object closer to the focal point, okay, and keep the height, for example, you put it in here, what happens is that the F ray is going to make an even larger angle with the principal axis. And with that, you will hit the mirror at an even higher point. Okay. And of course, it will be a parallel light after reflection, but then this extended line will have a larger height. Okay. So this tells us that, again, this P ray is always the same. Okay. This tells us that P ray and F ray will converge at a point that's even higher than Q prime. Okay, so if you move the object closer to the focus, you're going to generate a larger virtual image. Okay, okay, so this is what we talk about in this table, right? If you put the object just inside F, we see that the object is upright. And if you put the object between the mirror and F, you can see the object is also upright. It's an enlarged object, but if you move it closer to F, it will approach infinity. Okay, if you move the image, if you move the object closer to F, but keep it inside F, the image is always going to be virtual, always going to be enlarged, but the image is going to be larger and larger. Okay, we can derive all those by ray tracing. Okay, so we just learned that we can derive the position, the orientation, and the size of the image by ray tracing. Okay, so we know a few rays, we know how they will operate, and that will tell us where they converge conveniently. But can we describe the size, the position, and the orientation of image more quantitatively? So this is the derivation of mirror equation. Okay. So let's say we have an object in here. This is the red object. It has a height of h sub o. O means object. Okay, and we put it in front of this concave mirror. Okay, so as we know that this object will form an image somewhere, and the image is going to be inverted. Okay, so if we connect the point A of the object and the point B, the point B is where the principal axis crosses the mirror. This light ray is going to be reflected, right? And the angle of reflection is going to be the same as angle of incidence. Okay, so the reflected light will go through the image. Okay, go through the image, and we say that the image has a certain height of h sub I. Okay, and because image is an inverted image, we say that hi is smaller than 0. or in other words, if we talk about height, it is just minus hi, right? Minus hi. Now the question is that if we were given the object height, size, ho, and we place the object as a fixed position, so we know the object distance do. Object distance is the distance between the object and the mirror. Can we figure out quantitatively what is hi and where the image is? So what is di? Okay, di is the image distance, the distance between the image and the mirror. Okay, so we need to do some geometry because we're talking about geometrical optics. Okay, the geometry here is that we have two similar triangles. Okay, those are those two green triangles. Okay, so we can see that easily. So first, there is angle of incidence and angle of reflection, and those two angles must be the same. Secondly, we can draw this vertical line between point A and the principal axis and point A prime and principal axis, and they make a right angle here. Okay. So now that if we have two triangles with all the angles the same, then they are similar triangles, right? So for similar triangles, we can set up this kind of equation saying that uh, this side is divided by this side, okay, for this first triangle, top triangle, is the same ratio as corresponding sides. Okay, so the corresponding sides to HO is actually HI. So, and we know that HI is smaller than 0 because it's an inverted image, so we use minus HI in here. Minus HI here. So this is the bottom triangle. And it's minus HI divided by this side. Okay. And this side is just the image distance, the distance between the image and the mirror. Okay. So HO divided by DO is minus HI divided by DI. Okay, so from there we know that HO divided by minus HI is DO divided by DI. But this equation is not enough because we know where we put the object and we know the size of the object, but we don't know the height of the image and the height and the position of the image, right? So we have two unknowns and we need two independent equations. Okay, so to have this second equation, we keep observing, we find a second set of similar triangles. Okay, so this is about the C ray. Okay, so if you draw C ray, you connect the point A and the center of curvature C. You extend it, and it will hit the mirror at the right angle. Okay, so this image is this light ray is going to be reflected towards the same direction, and it will hit the image somewhere. Okay, and we can again see that those two angles phi are same, and then there are two right angles, and then the third angle are of course the same. Okay, so those two orange triangles have the same angles, and again we can set up the ratio equations. So on the left triangle we have HO, and on the right triangle, let's see, the corresponding side is HI, right? And again, this is an inverted image, so we have a convention that HI is smaller than 0, and if we talk about the size of HI, it's just minus HI. Okay, the second side we care about is this side. This side, what's the size? So we know that the distance between the object and the mirror is just DO, and the distance between the center of curvature and the mirror is just R. Okay, so the side we care about is just DO minus R. Okay, and the corresponding side on the similar triangle is this side. Okay, so how do we figure out this side? So the distance between center of curvature and the mirror is R, and the distance between this image and the mirror is DI. Okay, So the size of this side is r minus di. So we can set up this kind of equation for those two orange similar triangles. HO is here divided by DO minus R is here. This is basically, what is it? Tangent phi, right? And it's equal to HI minus HI here, divided by R minus DI, which is here. Okay, so this is also tangent phi. So from here, we know that HO is known, okay, DO is known, DI is unknown, and HI is unknown. R is known if we were given a mirror, okay? So we have two independent equations, and we can solve those unknown variables. Okay? So we have a first set of similar triangles, okay, this kind of ray connecting the object and the point that the principal axis crosses the mirror. And we have a second set of similar triangles for this C rays. And then we have two sets, a set of equations. Okay. So in this set of equations, HO is known, DO is known, HO is known, DO is known. Radius of curvature is known, and we need to solve HI and DI, right? So two equations, two unknowns. Okay, so what we can do is that we find out that DO over DI is HO divided by minus HI. Okay, and on the other hand, HO divided by minus HI is also DO minus R divided by R minus DI. Okay, so from there we find out that HO divided by minus HI is both this and this, right? So in this equation, we have only one unknown, okay, which is this DI. Okay, we canceled HI in here. And we further divide both sides by DO and multiply both sides by DI. Okay, we get this kind of, arrive at this kind of equation. R divided by DO plus R divided by DI is 2. Okay. And one more step to make it more general is that we notice that we can divide both sides by R. So on the right hand side, we have 2 over R, or in other words, 1 over half R. Okay? And we notice that half R is just the focal length. So this is just 1 over F. So we arrive at this mirror equation. Okay? This mirror equation is 1 over DO plus 1 over DI is 1 over F. Okay? DO is object distance, the distance between the object and the mirror. DI is the image distance, the distance between the image and the mirror. And F is the focal length. Okay, so for a spherical mirror is half R. So in here, usually we know where we put our object. So we know DO, we know the mirror we're using, so we know focal length F, and from the equation we can solve DI. Okay, and so we derived this mirror equation with respect to the concave mirror, and it is actually a very general equation if we get all the signs correct. Okay, so DO could be positive or negative, DI could be positive or negative, and F could be positive or negative. And with that kind of generalization, the mirror equation actually applies equally well to a concave mirror and a convex mirror. While if you talk about convex mirror, you need to use a negative focal length. Okay, so remember the focal length for convex mirror is half R, but there is a minus sign. Right? Okay, so we can do some exercise in here. So this is a concave mirror in here. We know the focal length is 5, right? Focal length is 5. This is f. And we were given different object distance, dO. Okay, so d sub o could be 25, 9, or 2. Okay, so the focal length is 5, and the distance between C and F is also 5. So if the object distance is 25, this tells us the object is beyond point C, right? So this is figure A. If the object distance is 9, it tells us that it is between C and F, right? So this is figure B. And then if the object distance is just 2, this is telling us that the object is within focal point F. Okay, so we solve the equation for DI. Okay, so where's the equation? This is the mirror equation. We know DO and F. We want to solve DI. What we do is that we find out that DI, 1 over DI, is basically 1 over F minus 1 over DO, right? And furthermore, this is F times DO, and the denominator is DO minus F. Okay? So if you solve DI, you find out that this is F times DO divided by DO minus F, right? Okay, so F times DO divided by DO minus F. Okay? And this is a concave mirror, so the focal length is positive 5. Okay, positive 5. And we plug all the numbers in. Okay, we plug all the numbers in, we find out that DI for the first case is 6.25. That tells us that this image is between point C and point F. Okay, because this is 5, but the image distance is 6.25. Okay. And in the second case, we find out the image will actually be formed beyond C. Why? Because the image distance is 11.3. Okay. But the radius is just 10. Okay, 2 times 5. So if you put object between C and F, you will have an image beyond C. Okay. In the third case, we have a DI of 3.33, and it is a negative value. Okay. Why does that happen? Because if you put the object inside F, okay, although you have a positive DI, you will form image on the other side of the mirror. So you have a negative DO, have a negative DI, negative DI, sorry. You have a positive DO and a negative DI. Because now you form a virtual image of the other side of the mirror. Okay, and we can find out that this distance between the image and the mirror is just 3.33 centimeters. Okay. Okay, another exercise. Now we have a convex mirror. Okay, and we know the radius of curvature is R is 20 centimeters. Okay, and we were given object distance of DO equals 6.33. Okay, so we need to find out the image distance. Okay, so we plug all the numbers in. Remember, you have a convex mirror. So for convex mirror, the focal length is minus, right? It's minus 10 centimeters, minus half R. So you plug in this minus 10 into here, you find out that DI is actually minus 3.88. Okay, what does that mean? That means that for a convex mirror, again, all the light rays will come in and then it will be reflected, and the reflected light rays are actually diverging. Okay, but it looks like they're from the same point behind the mirror, and that is where the image is. Okay? And the distance between the image and the mirror is the image distance is 3.88 centimeters. there is a minus sign because the image is a virtual image. Okay, it is on the other side of the mirror. Okay, and we just solved DI. Okay, there's another variable, unknown variable of HI. So that tells us the size of our image. Okay, so if we solve DI, we can plug in this equation. In this equation, we have DO and HO is known. We solved DI, then we can solve HI. Okay, HI is just minus DI over DO multiply by DHO. And we further define a magnification. Okay, so magnification is just H sub I divided by H sub O. So basically, you have an object, the size is HO, and then you form an image, the size is HI, and you want to know the ratio between the image size and the object size. Okay, so this is the magnification. And there is a sign in here. Okay, the sign of the magnification tells us the orientation of the image. Okay, for example, if you have a concave mirror, you have a real image. So DI and DO are both positive. So this magnification is smaller than 0. Why? Because the image is an inverted image. Okay. Now, if you have on the other hand, if you have a convex mirror, okay, a convex mirror, you can have, sorry, convex mirror, you have a real object, but then you have a virtual image. Okay, so DO is positive, DI is negative, this magnification is positive. Why is it positive? Because you have a real image. It is the same orientation as the object. Okay, although it's smaller than 1, it is still larger than 0 for the convex mirrors. Okay. Okay, so it is in here. So for the concave mirror, okay, the concave mirror, we can see that DI is positive. Okay, image is on the same side of the mirror. So mirrors image is in front of the mirror. So D of I is positive. Okay, so we have two positive values and there is a negative sign, so it's smaller than 0. So it tells us that the magnification is negative. Image is inverted. Okay. Same thing in here. The DO is positive. DI is positive. The image is inverted. Okay. Magnification smaller than 0. Now, if we have a convex mirror, again, you can do this ray tracing. You figure out where the image is. You'll find out that the object distance is positive. DO is positive. Image distance is negative because we have an image on the other side of the mirror or behind the mirror. So this is negative. And then there's a negative sign. So this thing is positive. Tells us that the magnification is positive, the image is upright. Right? Same thing if you have a concave mirror and you put your object inside F. Okay, put your object inside F. The light rays reflected by the mirror will be diverging. This is diverging, as you can see. But then you can extend the lines. They form a virtual image behind the mirror. The virtual image, the object distance is positive. Image distance is negative. Image is upright, right? So here is a summary of the sign conventions. Okay, so if we have a concave mirror, okay, concave mirror, concave mirror looks like that. You can have a object in here, image in here. So F is positive. Okay. You have a convex mirror. You have object in here, virtual image in here. F is negative. Okay, F is negative. So this is basically half R. This is basically minus half R. Right. And then magnification. Okay. M is positive for upright images. The image will be the same orientation as the object. M is negative for inverted images. The object is opposite direction as the object. The image is opposite direction as the object. Okay. Image distance. If the image is formed in front of the mirror, or is a real image, then it's positive. Okay. So remember, the light either is concave mirror, convex mirror, or plane mirror. The light ray can never go to the other side of the mirror, right? So if you have light ray converge on in front of the mirror, okay, in case of this is a case of the concave mirror, then you have a positive DI, okay, and you have a real image, okay. And DI is negative for image behind the mirror. Okay, so if it appears that the light rays are converging on the other side of the mirror, then it must be a virtual image, right? Because the light ray cannot cross the mirror. Okay, so it has to be a virtual image, then the image distance is negative. Okay? And furthermore, we can talk about object distance. Okay, for now, we have only talked about the object that is in front of the mirror. Okay, in other words, it is a real object. And in that case, we talk about the positive DO. Okay, but we can also imagine that we can have light rays, for example, for a plane mirror. Okay, we can have light rays converging on the other side of the mirror. Right? In this case, we will have a virtual object. Okay, for a virtual object, DO is negative. Okay? And as you can imagine, all those light rays will be reflected and then it will converge onto some point inside, in front of the mirror. Okay, so the image distance will be positive in this case. Okay, so you can have virtual objects and then DO will be negative in that case. Okay. And the last thing we want to talk about is when will a spherical mirror become a plane mirror, right? So a spherical mirror will behave like a plane mirror if the radius of curvature is very large or if the object is close to the mirror. Okay, and then we go back to this mirror equation. If R goes to infinity, F equals half R will also go to infinity. And then this is concave mirror. 1 over F will go to 0. 1 over DO will be minus 1 over DI. And DI will be minus DO. Okay, what does it tell us? It tells us that this is a plane mirror, right? For a plane mirror, you can have a real object. DO is positive, and then you will form a virtual image. DI is negative, and the distance is the same. Okay, so DI is minus DO. Okay, this is DO, and this is minus DI. This is a plane mirror. So the mirror equation works for plane mirror, works for concave mirror, also works for convex mirror. Okay. Okay. The last thing we want to cover today is the refraction of light. Okay. So again, this is part of geometrical optics. We say that the light is going along straight lines, but there is a little bit difference in here. Okay, so in here we talk about light going through different mediums. And although inside each medium, light is going along a straight ray, at the interface, the light can be bent. Okay, so that is the refraction of light. Okay, so to understand the refraction of light, we talk about the speed of light. Speed of light actually depends on the medium through which it travels. Okay, so we learned that the speed of light in vacuum is a defined value. Okay, it's about 3 times 10 to the 8 meter per second, or 300,000 kilometers per second. Okay? And we actually learned that it is an exact value, right? This is because we defined meter in the SI unit with the speed of light. Okay, so we define the meter so that the speed of light is exactly this much. Okay, so but this is only the speed of light inside vacuum. Okay, if you have light propagate inside a medium, the light is gonna slow down. Okay, for example, if the light is propagating through water, then the speed of light is c divided by 1.33, and the speed is smaller than the speed in the vacuum. Okay, so we can invent this physical quantity called index of refraction, represented by lowercase n, and it is a material property and tells us how much speed of light is slowed down inside that medium. Okay, so it is defined so that the speed of light inside the vacuum, v, is speed of light inside vacuum divided by index of refraction, n. Okay, so v is the speed in the medium, c is the speed in the vacuum, and n is the material or medium property. For example, for water, n is just 1.33, and the speed of light in water is just c divided by 1.33. Right? So as you can see, that index of refraction is just a number. It doesn't have a unit. And both c and v has the same unit of meter per second. Right? Okay, so now we have index of refraction, which is a material property. We can list it for all the materials. Okay? So it should include this material called vacuum. So for vacuum, n equals 1. This is very important. It's something you should know. Okay. Now, if we have air or carbon dioxide, the light is slowed down, but not too much. Okay, so still close to 1. If you have water, again, light is slowed down by 1.33 times, and for glass, it's about 1.5. Okay, this is a nice value to keep in mind. Okay, so in glass, the speed of light is just c divided by 1.5. Okay, now you have diamond, you can slow down the light even more. So light in the diamond travels at the speed of c divided by 2.4, right? Something like that. Okay, so the fact that the light moves at different speed at different media will give us uh, this phenomena called refraction. Okay, so refraction is when light travels from one medium into another, the speed of light will change, and then the light rays will bend at the interface. Okay, so for example, we have this green medium, medium 1, it has index of refraction n1, and we have this brown medium, medium 2, it has index of refraction n2. Okay, and inside each medium, the light again is going along straight lines or light rays. But we can see that at the interface, the light ray is bent. Okay, so how do we derive this? How do we derive this? So derive this, we again draw the, um, we recover the wavefront from the light rays. Okay, So remember that wavefront tells us where the peaks of magnetic field or electric field at a given time is at, right, in space. Okay, so for example, the light ray travels in medium 1. It is a plane wave, okay, at a certain given time. This point and this point basically the same, okay, just shifted by a distance. Okay, now let the light keep traveling. This light on the bottom will travel in medium 2, but light on the top will travel in medium 1. So they will travel at different speed, v1 and v2. And if you give it a certain amount of time, delta t, then the light will travel at different distance. Okay, so light in medium 1 will travel by this distance v1 delta t and arrive at point B. Okay, the light in medium 2 will travel by distance v2 delta t and arrive at this point. So as you can see that the wavefront actually shifts its angle. Okay, initially in the medium 1, the wavefront is in here, but then after it goes through the interface, the wavefront is inclined compared to the original wavefront. Okay, so now if the wavefront is inclined, we know that the light ray is always perpendicular to the wavefront. The light ray in medium 2 will also travel at a different angle compared to the light ray in medium 1. Okay, so how do we describe this quantitatively? Okay, so we look at this distance AB. Okay, point A is in here, point B is in here. Okay, and we can express it in two ways. Okay, first of all, we notice this point. First of all, we have an angle of incidence theta 1. Again, we have an incident ray. We have a surface normal. And the angle between the incident ray and surface normal is the angle of incidence. Okay, and after the light goes through the medium 2, we have another angle, the angle of refraction. Again, we talk about the light ray and the surface normal, and they make an angle theta 2. Okay, so we want to know the relationship between theta 1 and theta 2. We know that they are not equal. Okay, but what's the quantitative relationship? Okay, so we find out that for because this is a surface normal, so this is a right angle. So this angle is 90 degrees minus theta 1. Okay, and again, this is the green line is wavefront, the blue line is the light rays, so this is a right angle. So this angle is theta 1, right? So again, the green line is a wavefront and the blue line is a light ray. They're both in medium 2, so this is a right angle. So this angle will be 90 degrees minus theta 2. Okay, and again, this is a surface normal, so this angle is 90 degrees minus 90 degrees minus theta 2. So this angle is theta 2. Okay, now that we derive that this angle is theta 1, this angle is theta 2, we can look at sine theta 1 and sine theta 2. Okay, so sine theta 1 is this side, v1 delta t, divided by this side. Okay, this side is just AB. And then sine theta 2 is this side, v2 delta t, divided by this side. This side is AB. Okay. So now if we write 1 over delta t over AB, we find out that we can express it in two ways. Okay. The first expression, it has sine theta 1 divided by v1. In the second expression, we have sine theta 2 divided by v2. And again, v is just c divided by index of refraction n. So v1 is just c divided by n1, v2 is just c divided by n2, and we arrive at this equation. Okay, so in this equation, c is known, n1, n2 is known, and if we know theta1 angle of incidence, we will know theta2, the angle of refraction. Okay, so we further clean up this equation. We get n1 sine theta1 equals n2 sine theta2. In other words, during the refraction process, n sine theta is a constant. Okay? So in medium 1, n sine theta1 is equal to median 2, n2 sine theta2. Okay? And if it's air, then n1 is basically 1, and n2, if it's water, is 1.33. So we basically have 1 sine 60 degrees equals 1.33 sine 40 degrees. Okay. So from there, we know that if we have a light ray in air, it hits the interface of air and water, it will be refracted, propagating towards a different direction, and it's different from this dashed line. It is this blue line, and it's making an angle of 40.6 degrees with respect to the surface normal. This is a surface normal. Now, if we have a diamond, if N2 is diamond, so N2 is 2.4, then we have 1 sine 60 degrees equals 2.4 sine 21 degrees. Right? So we can derive where the light goes inside the diamond after it is refracted at the interface between air and diamond. Okay. And what we can observe in here is that since n sine theta is a constant with a larger n, you have a smaller sine theta and a smaller theta. Okay, so in the vacuum where the n is 1, you have largest angle. Okay, you have largest angle. And if it goes to a medium with a larger n, then it will have a smaller angle. Okay, have a smaller angle. Okay, so that is the properties of refraction from this law of refraction, right? So n1 sine theta 1 equals n2 sine theta 2. Okay. So if the ray of light enters a medium where the index of refraction is larger, so if the index of refraction is larger, then sine theta will be smaller. Okay, sine theta is smaller than theta is smaller, and theta is the angle between the light ray and the surface normal, so the ray will be bent towards the normal. Okay, so if we go back, we see that the ray, if there's no refraction, will go this way, and it bends towards the normal. Okay, the ray will go this way, but then diamond has a larger end, so the ray bends towards the normal. Okay, or in the medium with a larger end, there will be a smaller angle with respect to the surface normal. There is no change in the direction of propagation if there's no change in the index of refraction. In other words, inside the same medium, n is a constant, so theta is constant. So inside the same medium, the light ray is going through a straight line, right? And if there is a smaller change in the direction of propagation, if there is a smaller change in the index of refraction, okay? And if the ray of light goes from one medium to another along the normal, then it is not deflected, regardless of the index of reflection. Okay, this is because n sine theta 1 is, this is because when you go normal, then theta 1 is a 90 degree or 0 degree. Remember that angle of incidence is always defined as the angle with respect to the normal direction. Okay, So if the light ray goes through the normal direction, then theta 1 is 0. Theta 1 is 0, sine theta 1 is 0, and then sine theta 2 is 0, and so theta 2 is 0. Right? So if the light is going along the surface normal, you will keep going along the surface normal, and you will not be bent. You will not be bent. Something like that. Okay, we have a demonstration. This is telling us that if we have a variable index of refraction, how would light travel? So in this case, we have a laser pointer in here, and then we put some sugar, okay, inside this tank. Okay? And after we put the sugar in there, okay, we make the sugar flat. And then we pour in some water. Okay, so the sugar will be dissolved in water to make a saturated solution. Okay. So initially, before the sugar is dissolved, we see that the light is going through a straight line. Okay. Now, let's give it a few days. Let's give it 3 days so that the sugar is well dissolved. Okay. Now we have a very dense sugar solution. Okay. And what happens is that the solution will be even denser at the bottom of this tank. Okay. So which means that we will have a larger n in here, and we have a smaller n on top. Okay. And now if we have a light ray that goes this way, okay, we know that the light ray will bend towards the normal if the n goes larger. Okay. So it will keep bent towards the normal. Okay. Something like that. Okay. So the light ray should go something like that. Okay. And does it actually go like that? We see that the light ray actually bent towards normal in the more dense solution, or in the larger index of refraction n. All right. Pretty good. Okay. So this is the application of the Snell's law inside the medium with a variable refractive index. Okay, and one of the consequence of this variable index of refraction is mirage. Okay, for example, if you're driving inside the hot weather, the road will look like a mirror. Okay, so how does it work? The road looks like a mirror means that the object far away from you reflects from the road. Okay, and then it forms an image. Okay, below the road, right? Because the road is like a mirror. So what happens is that you have a hotter air near the road, hotter air near the road. And when the air gets hotter, it will get less dense. And when it gets less dense, the N will be closer to 1. Okay. And for colder air, it will be dense, so N is larger than 1. Okay. So then you have a gradient of index of refraction like this. Okay. So if there is a car in there, there's a car in here, car is emitting some light rays. Okay. Every time it goes into a hotter medium or a medium with smaller index of refraction, it will always bend away from the surface normal. Okay? So if there's no refraction, it should go this way, but then bend away from the normal because we're going into a less dense medium. Okay, so it will keep doing that. It will make a trajectory like that. So it will enter your eye, and it looks like there is a perfect reflection. So the road looks like a mirror. So the light from the tree, if there is a hot air near the ground, then it will bend the light rays. Okay, if you bend the light ray, it hits your eye. It looks like it's emitted from a straight line of a object below the road. Okay, so this is a common mirage from the refraction of light. Okay. And we can solve this kind of questions. We keep in mind that during refraction of light, n sine theta is a constant, right? So if we have a medium n in here, so we have n sine theta in here, where theta is this angle, right? Now the light enters the medium 1, it will make an angle theta 1. And remember, n sine theta is n1 sine theta 1. Okay. And this is also theta 1. Okay. Now that the light enters medium 2, it will make an angle theta 2. And this constant is also equal to n2 sine theta 2. Okay. And so on and so forth. It is also equal to n3 sine theta 3, n4 sine theta 4. Right? And now if we have a more and more dense medium, so n increases, then the theta is gonna decrease. Okay, n increase, theta decrease. So n sine theta is a constant. So we see that the light ray is bent this way. Now the light ray will enter the medium n again, and which direction will be the light ray inside the medium n? So we know that n sine theta is a constant, so when it enters the median n, it will recover n sine theta, right? So that will be the original theta. So the original theta will be choice C, right? So this line and this line is parallel. This is from Snell's law that n sine theta is constant regardless of how many medium you're talking about. Okay. This is a very typical example of refraction. You have a pencil and it's inside water. And when you use eye to look at it above the water inside air, it will look like the pencil is bent. Okay. And it's bent towards you. So why is that? So if you consider some light ray emitted from the pencil, okay, it will go this way and it will hit the interface between the water and air, right? So air has a smaller refractive index, so n sine theta is constant, but n is smaller, so sine theta will be larger, so the angle will be larger in the air, or in other words, the light ray will bend away from the surface normal. So now if you use eye to look at it, it looks like the light rays emitting from the extended lines. Okay? So now if you extend the line, you will find out that the extended line will cross at the point that is higher than the original pencil. Okay, so the pencil will bend, it will look bent, and it will bend towards you because the water has a larger refractive index than the air, right? Okay. This is another situation. You have a slab of glass and you have light propagating through it. So you have basically n sine theta outside the glass. Theta is this angle of incidence, and then it becomes this angle alpha in here. Okay, so n sine theta is n glass sine alpha, right? And then you will make another angle of incidence alpha at another interface between glass and air, and then you will recover the angle theta because n sine theta is a constant. Okay, so it looks like the incoming ray and outcoming ray are actually parallel, but it looks like it's shifted uh, by a displacement. Can we actually calculate this, how much displacement is in there? Okay, first we have this Snell's law. We have n sine theta equals n glass sine alpha, right? So from there, if you know n of outside medium, if you know the angle of incidence, if you know the uh, 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 index of refraction of a glass, you can solve this angle alpha inside the glass. Okay, and from there you can. The second thing is that you probably know the thickness of this glass. This is, let's say, D. And from there, you can calculate the distance between the point A, where the light first hit at the interface, and the point B, where the light hit the second interface. Okay, so there is a triangle in here, and that right angle triangle. So AB equals what? So cosine alpha is D divided by AB. Okay, so in other words, AB is D divided by cosine alpha. Okay, and if you know the thickness of the slab, if you know alpha, you can calculate the size of AB. Okay, but now if we know AB, we can actually calculate BD. Okay, let's say we draw a straight line from B to the dashed line, and we say the cross section or point is D. Then there's another triangle in here. Okay, and let's say what's the angle in here. So this blue line is a straight line. This surface normal is a straight line. So this angle is alpha. Okay, and inside the triangle ABD, this angle is theta minus alpha. Okay, and we know AB, we want to know BD, and we know BD divided by AB is sine of that angle. Okay, so BD is AB times sine theta minus alpha. Okay, so as you can see, if we know the index of refraction of outside medium, we know the angle of incidence, we know the property of the glass, refractive index of glass, we know the thickness of glass, then we can calculate how much is the light ray is shifted sideways, and that is the size of BD. Okay. Okay. So here's a problem. A horizontal ray of light and encounters a prism, and after passing through the prism, is a ray deflected upward, still horizontal, or deflected downward? Okay. So again, we understand that we have a air outside the prism, so this is one, and the prism is made of a material that's probably with higher refractive index. So at the first interface, it should bend towards the surface normal. Okay, it should bend towards this way. And what about the second interface? The second interface is going from a larger refractive index to a smaller refractive index. So the angle inside air should be larger than the angle inside prism. Okay. And what happens is that the light ray is further bent away from the surface normal and from the horizontal direction. Okay. So in both reflections, first reflection, second reflection, light ray is always bent downward. Okay, the net result is that the ray will be deflected downward. Okay, ray deflects downward. Okay. A important special case of the phenomena of refraction is the total internal reflection. Okay, so we consider two mediums, and there's medium one refractive index is N1, medium two refractive index is N2, and N1 has a larger refractive index than N2, and the light is going from 1 to 2. Okay, for example, we can have water in here and air in here, and the light is going from water to air, right? And what happens is that because air has a smaller refractive index, so theta 2 should be larger than theta 1. Remember, n sine theta is a constant. Okay? Now, if we increase theta 1, theta 2 will also increase correspondingly. Okay? N1 sine theta 1 equals N2 sine theta 2. If we increase theta 1, N2 and N1 are kept the same, theta 2 will also increase. Okay? It will hit a special case where N2 equals 90 degrees. So the refractive light will go exactly along the interface in this case. And we call this angle theta 1 as critical angle theta C. Okay? C means critical. Now, if we keep increasing theta 1, we'll reach a situation where you cannot find a solution to this equation of N1 sine theta 1 equals N2 sine theta 2. Okay, why? Because now we have a theta 1 that's larger than theta C. And what happens is that N1 sine theta 1 divided by N2 is larger than 1. So you need an angle theta 2 that satisfies sine theta 2 larger than 1, and no angle can satisfy that. What happens is that when theta 1 is not larger than theta c, we cannot solve the equation and find theta 2, and there's no theta 2, and there's no refraction. And in that case, all the light will be reflected at the interface between air and water. Okay. And that is called the total internal reflection. Okay, it is a total reflection because there's no light going in refraction. It is internal because everything happens inside the medium one, the medium with higher refractive index. Okay, again, we can derive the critical angle. So critical angle is the angle where the angle of incidence where the angle of refraction is 90 degrees. Okay, so we plug theta 2 equals 90 degrees into Snell's law. Sine 90 degrees is 1, so right hand side is N2. We find out that theta c is defined by this equation. Sine theta c is N2 divided by N1. And N1 is larger than N2, so it is smaller than 1. Okay, so we can find a special angle called critical angle. Okay. What if N1 is smaller than N2? If N1 is smaller than N2, for example, we have air going into the water, then sine theta c will be N2 divided by N1, and N2 is larger than N1, so it's larger than 1, so there's no such theta c. Okay. So if light is going from a less dense medium into a dense medium, then there's no total internal reflection. Okay. Total internal reflection only happens if light is going from a dense medium to a less dense medium. Okay. And in that case, we can find out the critical angle, and when theta 1 is larger than the critical angle, then total internal reflection will happen. Okay. You can also look at this figure on the top left. Okay. We have different angle of incidence. Initially, there's always some refraction, but then if the angle is larger than the critical angle, all the light will be reflected inside the water medium. No light will go to the air. Okay. There's no refraction anymore. Okay, and this is actually very useful. For example, inside this uh, pair of binoculars, they actually use this special material with a given refractive index n, and they design the light path so that the light hits the prism at an angle that is larger than the critical angle. Okay, so what happens is that there is no refraction, and all the light will go through total internal reflection. And it goes through a few total internal reflections. There's one in here, second one in here, third one in here, and the fourth one in here. And this way you can change the light path from here to here, right? So if you have an object outside, you can actually image it into your eye. You can shift it by a certain distance and send it to your eye without losing too much light. Okay. Same thing inside the fiber. Okay. If you have an optical fiber, it is a carefully designed medium. Okay. So you have a core material has a N1, and the cladding material has a refractive index N2. Okay, and we have N1 larger than N2, so that when light goes from N1 to N2, there is total internal reflection. Okay, so in this way, no light will emit towards the cladding and into the environment and get lost, and you can transmit the light through long distance by a series of total internal reflections. Okay, so the fiber can guide the light through the fiber. Okay, sure. So with a fiber, you can change the direction of light as you wish, and you can extend the signal of light into a long distance without much loss because there's total internal reflection. Okay, and same thing happens in this mirage. Okay, in this mirage, again, there is a series of refraction, but at the interface, there is a total internal reflection, right? Because light is going from a dense medium into a less dense medium. Okay, so there could be a total internal reflection in here. And that helps the light ray goes through this path and helps generate a mirage. Okay, so this is an optical fiber, and we can see light go through several total internal reflections. And if you bend the fiber, there will be more total internal reflections, but we can still transmit the light through the fiber. Okay, so that's the principle of total internal reflection and optical fiber. Okay, so that's it for today, and next time we will be talking about forming images with lenses. Okay, thank you.